Hi, everybody. Welcome to another session of Dots. Today, we are very happy to start off with Jose Walteros. I don't know how to pronounce it.
That's perfect.
He'll correct me. He'll correct me. Dr. Walteros is an assistant professor in the ISD department at the University at Buffalo. He has his PhD from a very nice place, the University of Florida, where I happen to be located. And Dr. Walteros has extensive experience in developing exact and approximate solutions for solving a wide variety of challenging problems, including attacker-defender games, logistics, and many, many others that are listed on the abstract posted on our website. He has many awards that I can list briefly that he's been funded by the NSF, Naval Research Office, Air Force Research Lab, AFOSR, the Department of Transportation, and others. Doesn't all fit in the bio. He's also served as the president of JFIG at Informs and the vice chair for network optimization in the Informs Optimization Society. And his papers have appeared in a large number of prestigious journals such as OR, iJoc, Networks, Math Programming, and others. We are very happy to have Jose here today. Please take it away.
All right. Thank you, Alex, for the kind introduction, and thank you, Sylvia and Elias, for the organizing this. It's a pleasure for me to be here, and thanks everyone who joined the presentation. So I'm given the challenging task to go before David, who's going to talk about a very exciting topic, which is sports betting. So I think that I'm going to take this opportunity to hopefully attract some of the people who are interested in that into the area of interdiction, which is quite nice. So this is talk about a general class of multi-stage interdiction games that have some interdependencies. And part of the research that I'm going to present today was funded by Air Force. So I want to thank them for the support as well. So give me 1 second. Let me set up my timer here so that I can go over. All right, so let's begin. So let's begin with some preliminaries. So this is in general like the main definition that I can give about these type of games. So these interdiction games, multi-stage games, try to model an adversarial, finite, sequential, and alternating interaction between two decision makers that we typically refer to them as the attacker and the defender. So graphically, what you can see is that typically what happens is that one of them begins. Let's assume that the attacker begins. The attacker solves an optimization problem, finds a solution, and uses that solution to parameterize the optimization problem of the defender, which plays in the next stage. The defender then again solves another optimization problem, finds a solution, parameterizes the same model, and this continues until the end of the game. The two most common versions are obviously the two-stage game, where you give only one stage for each of the players. The attacker typically plays first, and the defender. Also, something important, sometimes people, instead of referring to the defender as the defender, sometimes people refer to it as the operator. I'm going to use defender for the context. And the other type of game, of course, that is you can find a lot of papers on that too, is the three-stage version, which is the case where you give the defender another stage before the attacker. And what the defender, of course, tries to do is to somehow mitigate the effect in the attack. Often people refer to this game as the protector, attacker, defender instead of defender, attacker, defender. In this presentation, I'm also going to use the name protector for the three-level games so that it's easy for me to differentiate the two stages that the defender plays. Again, also people use operator, but I'm going to stick with defender. I'm going to focus on the first two, these two common versions, and later I'm going to show you how to extend the solution techniques for the three-stage version to longer games. So let's begin with two games. So first, I'm going to start with some notation that is going to appear in most of the formulations that I'm going to use. So the first thing is that I'm going to define delta to be the ground set of the game. So essentially, it's the set of elements that are going to compose the solution of the attacker and the defender. I'm going to say that phi is the solution space of the attacker, and by convention, I'm going to call the solutions of the attacker strategies. So whenever you hear me talking about a strategy, that means that that's a solution for the attacker. And I'm going to use omega in reference to the solution space of the defender. And I'm going to refer to those solutions as structures. So the reason why we typically refer to this, or like I refer to this as structures, is because in a lot of cases, these interdiction games are staged on networks. So typically what happens is that the defender wants to build some sort of like a construction on the network, like for example, a short span, a spanning tree, a dominating set, vertex code, or some other structures like that. So whenever you hear me talking about a structure, that is a solution for the defender. So for this reason, of course, every time you give me a solution of the game, is gonna be a pair. I'm gonna refer to this as the UT pair, where U is a strategy and T is a structure. And of course, it's just a member of this cross product between the two solution spaces. I'm going to refer to as this omega of U, the set of structures that are gonna be blocked by an attacker strategy U. I'm going to be more specific about what we mean by blocking or a solution being blocked by a strategy in a second. But for now, let's assume that those are the structures that will not be able to be used by the defender if the attacker uses strategy. For the defender, I'm going to use a weight function W that essentially is going to tell us how good the structure is for the defender. The structure chosen by the defender, how good it is. It's just basically a weight function. For the most part, it's a linear function that adds the weight of each of the individual elements of the structure. Like, for example, if you have a short span, it just essentially adds a value for each of the edges of it. And for the attacker, I'm going to define this function C, which is again a measurement of how good the strategy is. For the attacker, we use weight for the defender, cost for the attacker. I'm going to assume also for, without loss of generality, that the followers or the defender optimization problem consists of finding a structure of minimum weight. So always the defender would like to find a structure that weights the least. So in terms of the type of games that you can play, there are two specific structures that you may have. This one, which is the budget game, is the one that is most used. Like a lot of people, most of the papers into stage interdiction use this particular structure. And is the case where the attacker is given a particular budget. It has a budgetary constraint, and what the attacker wants to do is to maximize the weight of the structure chosen by the follower. So as you can, or the defender. So as you can see, the attacker finds a specific strategy U and parameterizes the optimization problem that tries to find the structure. So essentially, the defender can only find structures among the structures not interdicted by the follower, by the attacker, and the attacker has this budget. But you can also have a different type of game in which you kind of like reverse the objective and the constraint of the budget game. In this particular case, instead of having a budget, what the attacker would like to do is to minimize the cost of inflicting a certain disruption on the defender. So the way it works is that the attacker is given somehow a target R of the weight of the structure of the follower that wants to reach. And it would like to minimize the cost of ensuring that such a weight is at least a particular value R, right? So the disruption is essentially, again, raising the weight of the structure chosen by the defender. One more thing about the categorization of the games that we're playing here. I'm going to assume that the ways are binary. Binary in this case, I don't necessarily mean a 0-1 game, but I mean something slightly different. The idea is the following. If you have a strategy structure pair, U and T, I'm going to say that these two solutions interact with each other if the intersection of them is non-empty. So essentially, an attacking strategy or like interacts with a structure of the follower if the attacking strategy uses at least some of the elements used by the structure. So we say that the game is binary if this interaction means that the defender will no longer be able to use that particular strategy. So in the context of an interdiction game playing on a network, what this essentially means is that if the attacker chooses a set of vertices, let's say, what happens is that the defender will no longer be able to use any of those vertices or the edges used, which means that any structure that contains one of those elements will not be able to use by the attacker. Most people use the name also total or complete interdiction for this variation of the game. An alternative of this will be a situation in which instead of removing the element from the game, you raise its weight, for example, right? So the difference is that the strategy in that case will raise the weight of some of the elements, which means that the structures remain in the graph and might be used still by the defender, right? So we're not interested in that. We're interested in the case where we literally just essentially block the structures from being used. So perhaps the most common approach to solve this problem is known as dualize and combine, the dualize and combine strategy, which only works when the solution space or the problem of the defender has somehow a convex representation that you can actually dualize. So typically what people use is that you have a problem that is linear or somehow convex. You can replace this component by its dual, and then you can solve a single level reformulation. Similar way you can replace this by its dual, and it becomes a single level reformulation. For the sake of generality, I'm not going to consider this this solution approach, mainly because we're going to consider more complex defender problems that cannot be dualized, right? So we can have problems here that are, let's say, NP-hard, like a dominating set problem or something like that. So we cannot use this technique. So I'm going to consider more general methods that are typically called enumerative methods. So whenever you see an interdiction presentation, people typically use the shortest path interdiction game. So it's the kind of like the gold standard for presented interdiction. I'm going to break the mold. I'm going to try to use a different game. I'm going to present to you a game that is known as a dominating set interdiction. So the idea is that the defender wants to find a dominating set and the attacker wants to disrupt the dominating set. Okay. So if you're not familiar with a dominating set, it's just a general graph construction. The idea is the following. If you're given a graph with a set of vertices and edges, a dominating set is a subset of vertices such that every vertex in the graph is either in the dominating set or is adjacent to one of the vertices in the dominating set. So in this example, for instance, if you pick the red vertices as your set T, these vertices represent a dominating set in the graph. If you notice, every black vertex is adjacent to one of these red vertices. Dominating sets are typically used in the context of communication. If you think about it, if you want to be able to communicate with every vertex in the graph, you can place an antenna in the red vertices and you have one hop communication with everyone in the graph. So that's kind of like what most people use dominating sets in the context of communication. So in the interdiction game, what happens is that the attacker is going to block some of the vertices. So for example, the attacker can decide to block these two vertices. Importantly, that doesn't mean that it's going to remove the vertices, because that could potentially help the defender. What it will do is just block them. So you have to still cover them as the defender, but you cannot place an antenna there, or you cannot use them as part of the dominating set, right? So if the attacker chooses these two blue vertices, then now the defender cannot use them, so it's forced to use other vertices. If you notice, in this particular case, the solutions are optimal. What happens is that the attacker forced the defender to pick a bigger dominating set. Before it was 3, now it has 4 vertices. Okay, it's kind of like the idea. All right, so let me talk about really quickly about the reformulations that people use to solve these problems. If you're solving a target game, typically the reformulation that you use is going to be looking something like this. So let me show you what this means. So this set omega sub r is the subset of structures, like dominating sets, for example, that have a weight less than r, right? And since our game is binary, meaning that you need to interdict at least one element from each of those dominating sets that you want to target, because they have small weight. So the attacker solved this game, which is a set covering problem, essentially, where for each of those structures, you force the attacker to interdict at least one of the elements of each of them, right? So we actually show at some point that any target interdiction game that has 2 levels can be reformulated as a set covering problem like this one. The main issue, of course, is that the number of constraints that you need to use could grow exponentially. And also, if you want to solve this with a lazy constraint, though, the constraint generation, the issue is that the separation problem is essentially solving potentially a hard problem. Like in this case, we'll be solving a dominating set. For the budget game, you can do something similar. I'm going to focus on this formulation, even though there's another one. So just to explain really quickly what this formulation is, if you just focus on this part of these constraints, what this formulation does is that it creates a constraint like this one for every structure of the game. So if these are dominating sets, for every dominating set, I'm going to create this constraint. So if you look at this part of this formulation, what this formulation does is actually finds the dominating set of minimum weight, right? So essentially you try to maximize W, but W is upper bounded by the weight of every dominating set. So obviously if you don't have this part, this formulation finds the minimum dominating set. And if you introduce this part, what this means is that if you interdict at least one of the elements of that structure, you don't need to count that in this bound. And of course, you have the budget. So similarly to this constraint, this reformulation has an exponential number of constraints that you have to solve sequentially if you want to solve this for a relatively like medium-sized, large-sized problem. And again, this separation problem could be difficult. It could be an NP-hard problem. This
Question.
Yes, go ahead.
So is the first formulation for the budget game, is that similar for the budget one?
This one, yeah. So the budget game, the second one, there's an alternative formulation to this one that is very similar to this target game. It's actually more than it's a feasibility problem that you can. But I want to skip this one so that I can go over the.
And is the first one equivalent to the usual the budget game, the first budget game formulation? Is the budget game one equivalent to the value function reformulation that people use it by level programming?
Yes, this is kind of like a value function essentially. Yes, absolutely. This is literally just essentially value. Yes, absolutely. All right, cool. So now really quickly, let me go over to the three stage because I'm actually running out of time. But the idea is similar. I'm going to keep the same ground set. I'm going to assume that the protector now, which is the player who plays first, has the same ground set. And I'm going to call the solution as the policy set. So we have policy, strategy, and structure. And I'm going to call the solution space gamma. Now we have a triplet. S is the policy, U is the strategy, and T is the structure. So in a similar way, since now the protector is going to block some of the policies of the attacker, so I'm going to say that pi of S is going to be the set of strategies blocked by the protector structure. And I'm going to assume that the protector and the attacker also have like this binary property. And similarly as the attacker and the defender, the protector is also going to have a function weighing or measuring the quality of the solution. In this case, I'm going to call this function the price. So what types of games we have when you have three stages? So again, this one is the most common one. This one is the one that has appeared in most of the papers. It's a min-max mean problem. And the idea is that it's a budget game. So the idea is that you give the protector and the attacker both budgets. And what the budget of what the protector wants to do is to minimize or mitigate the disruption on the objective of the defender. It's kind of like the idea. I'm going to talk about this one later in more detail. But you can also, considering that you have target versions of the two-level game or two-stage game, you can also do something like this, which is a target game, in which the protector would like to minimize the cost of ensuring that the cost of an attacker is at least a certain value R, of raising the weight of the structure chosen by the follower up to a particular value R. And of course, you can have any combination of budget target or target budget. I have not seen any of these two in the literature yet, but there are some interesting applications for them as well. So I'm going to concentrate in these two versions, which are the ones that appear in the literature the most. And again, just an explanation of the stage level. So in the context of the dominating set, the protector now is going to fortify some vertex. So what that means is that the attacker will no longer be able to attack this vertex. So it's going to have to attack some other vertices, and sometimes this could result again in a solution for the defender that is better than before. So in this case, notice that the defender was able to, again, only use 3 vertices for the dominating set. So what are the solutions approaches really quickly? So what most people do is understanding that there is an underlying 2-level game in the 3-level game. So what this essentially means is that if you look at this component, this is the attacker-defender component, you can reformulate this as a defender, right? So you can actually observe that the protector is actually an attacker who is attacking the attacker. So you can formulate the attacker-defender component as just as a defender component and the protector as an attacker, and just essentially use a similar strategy or similar formulation that we used before for solving the 2-level game. So this transformation is essentially noticing that the policies become now strategies for this 2-level game. And of course, the strategies kind of like become structured. So a structure in this nested reformulation is somehow a strategy of the attacker becomes a structure of the attacker. So let me give you a specific, you can also do this for the target game as well. Let me give you how this works in general. So in the context of the target game, for example, it's in this 3-level formulation. Typically what you do is that you solve this using this nested reformulation. So the way it works essentially is that now the protector has its set coding problem where you're trying to block attacks. So now this is just essentially the attacks that are generated, the strategies that are generated. You parameterize this part of the game with a specific protection strategy. This is the set covering problem associated with the attacker. And what the attacker does is that it provides an attack to the defender. The defender solves the dominating set problem, and you're going to create this loop generating constraints for the attacker until the attacker cannot improve the solution. So you find a solution for the attacker after doing this loop multiple times. You find a solution for the attacker, and the attacker parameterizes the defender a problem. You solve this problem, find a new protection strategy, give it to the attacker, and then you keep doing this loop until you find that the protector cannot protect this anymore. You can actually improve this strategy of solving these games by introducing something similar to what Lozano Smith proposed in the past, which is a sampling framework that is really good to manage these sets and avoid them to grow very, very quickly. So again, as I mentioned before, this is essentially kind of like an underlying attacker-defender game in the case that this is actually kind of like a nested defender game or a defender game that is solved as an attacker-defender game. So, and the nice thing about this nested structure is that you can keep the same idea when you have more than 3 levels, right? So essentially the way it's going to work is that you're going to perform this loop to find a solution for the attacker, then perform this big loop to find a solution for the defender in this stage, and then that's going to give you a solution that you will use in the attacker component here, and you keep doing this nested approach, go back. So it's something similar. You can see an analogy of what people do in dynamic programming, that you have some sort of like a forward pass, play around, and then just do a backward pass and somehow. So something like that. The issue with this, of course, is that the complexity grows very rapidly because each of these problems is actually very difficult. So you're going to start to generate a lot of constraints in each of these. Okay. All right. So really quickly, let me go. I'm going to go over this relatively quickly. Is what do we mean by an interdependent multi-stage interdiction game? So we're going to say that a multi-stage game is stage-wise interdependent if there's a direct interaction between solutions of 2 non-consecutive players. So what that means essentially is that if in the 3-stage game, for example, if you have a policy strategy structure, if the solution of the protector also interacts with the solution of the defender, and the defender is no longer able to use the strategy T, that means that this game is stage interdependent. So in the context of the presentation here, as you can see here, what happens is that now the 3rd level, which is the defender game, is actually also parameterized by this strategy. In the target game is the same idea. So to give you an example of a game like this, because you might be asking yourself why the protector is going to be interested in blocking the defender. Let me give you an example. So suppose that you're back in the interdiction problem, and whenever the protector decides to protect this vertex, let's assume that this vertex is no longer going to be able to be used by the defender. However, think about this as placing an anti-jamming device. So you place an antenna that is an anti-jamming device, the defender is not going to be able to use it. However, in some radius around this vertex, these other vertices in orange are going to be protected. So the attacker is not going to be able to attack these 2 vertices. So in some sense, what happens is that you pay a little bit of a price for placing an anti-jamming here, meaning that these vertex cannot be used by the defender, but you gain a lot because you are going to be able to block attacks in vertices surrounding the vertex that you choose. What is the problem with this? The problem with this is that this nested sequential formulation that I showed you before doesn't work. So the problem is not as simple as just essentially also using this protection strategy to parameterize this inner model. Because if you try to use it in this way, also parameterizing this, this formulation actually helps with very often with a solution that is suboptimal. And the reason is because the parameterization of this creates cuts that are depending on the previous strategies. So you need to do something different. So the strategy that I'm actually presenting here is very simple. So the first thing that we can show is that you can actually find a lower bound of that game by solving the problem, assuming that the protector strategy, the protector policy is not going to affect the defender. So obviously this is a lower bound in the sense that this could give you a solution that is infeasible. It will be a solution that the defender uses elements that are blocked by the protector. So this is a lower bound. You can use this as a lower bound. And then you can find an upper bound simply by passing the true attacker-defender game any static policy, and this will give you an upper bound. So you will be able to find upper and lower bound of these games. And what you can do is that you can apply a very simple branch and bound approach. So really quickly, the idea of this approach is something like this. Suppose that you solve the lower bound, which is this game here, right? And what you can try to do is to check or to do a feasibility test. The feasibility test is whether the defender uses a structure that is in conflict with the policy of the protector. So in other words, if the defender uses some item or some of the elements that has been blocked by the protector. If that is the case, that means that the solution is infeasible, so you're going to create two branches. In one branch, you kind of like accept the policy of the protector. So in other words, you fix that, so that means that you assume that the protector is going to fortify that item, but you forbid the defender to use that item. And in the other branch, you do the opposite. You forbid the protector to defend that particular item and allow the defender to use it. And you can create these branching strategies. So the nice thing is that this actually works in general for any of the versions that I discussed before. So some preliminary results, we implemented this for the target version of the game using Godot. And just a word of caution, like implementing this is kind of like difficult in the sense that if you want to use lazy constraints, one of the big issues is that Godot doesn't store the lazy constraints. So whenever you're inside of this loop, whenever you repeat the loop, if you're not careful, you're going to potentially enumerate constraints in the lazy loop constraint that you have enumerated before. So you have to somehow store them and then just populate them. The other issue is that the constraints that you're generating and each of these subnodes of the branch and bound tree are only local cuts, right? And I don't have time to explain why. But we have been able to solve instances between 20 and 300 vertices of this dominating set game that I showed you. The only issue is that the difficulty of the game depends on multiple things. Depends on the radius that I showed you before of the protection. It depends on the density of the graph. It depends on the capacity of the targets. But at least we have a specific strategy that works in any case. We're currently implemented one version of the game that has 4 stages, and the preliminary result seems to be fine. It works well as well. So I'm going to stop here so that I can give some time to David, but thanks a lot for joining, and I hope you guys enjoyed the talk.
Thank you, Jose. I think we do have time for maybe one quick question or 1.5 quick questions. Yes, Noah.
Yeah, I was wondering how you handle infeasibility, like if the dominating set problem becomes infeasible because of some action of the attacker.
Yes, so great question. So in that, there are multiple things that you can do. In that particular case, you can actually have a kind of you can change the weights to infinity. So in some sense, what that means is that this creates a dominating set that has an infinite cost. Yeah. So you can always find a solution that is infinity, and for the attacker that will be enough because it means that you raise the weight of the dominating set more than the target. But yeah, that's something that is true. You have to deal with infeasibilities as well.
Thanks.
And then I have a very quick question on slide 38. when you were showing this. So on the D branch or the defender branch,
Mhm.
are you forcing that I is going to be used by the defender,
No,
or just
no,
that
no,
it's
no.
not going to be a? Okay.
Yes, you only force that it's not going to be blocked.
So okay, perfect. Thank you. Okay, so then and then let's thank Jose one more time, and then we have also going to be we're also going to have a chance to talk to Jose afterwards in the breakout room. So please stick around if you want to chat with him, and yeah, please do stick around.